Welcome to a deep dive.
Hello.
Today, we're plunging into a topic that really feels like science fiction sometimes,
Yeah.
but it's making very real headlines. Nuclear fusion energy.
Yeah.
You've probably heard it called the artificial sun, maybe even the holy grail of energy.
Absolutely. It's the quest to basically replicate the power source of stars, but right here on Earth.
Huh.
And the potential payoff is just huge.
Right.
We're talking a virtually limitless supply of clean, high-powered density energy. It's definitely one of the most significant tech pursuits happening right now.
Couldn't agree more. And we've got a stack of sources here today that give us a really current snapshot of, well, where things actually stand.
Hmm.
We're pulling key insights from an interview with MIT's Dennis White that was in the Bulletin of the Atomic Scientists, and also some recent reports on major advancements out of China. Those are from places like CNNC, NAM.
Right, a good mix. And our mission today really is to take these sources and just unpack the most important nuggets. We want to understand the current global landscape. Who are the key players beyond that big international project everyone knows about, ITER?
Which we'll get to.
Yeah, and also get to grips with what these specific recent technical steps forward really mean for the future of fusion, especially, the possibility of actually getting this power onto the grid someday.
Get ready, because we're going to look at some, frankly, surprising details and hopefully gain some critical insights into this really intense, fast-moving global race for what could be game-changing energy.
Let's do it.
So for a long time, when people talk fusion, a conversation pretty much started and ended with ITER, didn't it?
It really did. ITER, the International Thermonuclear Experimental Reactor. It's this huge collaborative project being built down in France.
Colossal is the word.
Yeah, and the sources highlight it's got or will have the world's most powerful magnetic system. Its whole job is to confine that super hot plasma.
Right.
It's a massive scientific undertaking. They're aiming to start operations around, 2039?
Yeah, that's the timeline.
With the goal of basically proving fusion is feasible on a large scale, sort of paving the way for actual power plants later on.
And it involves, tons of countries working together. But what our sources are showing is that while ITER is undeniably huge, it's not the only game in town anymore.
Definitely not. And certainly not the only place where real progress is happening.
Okay.
If you look at the bigger picture, that bulletin interview points out something interesting about Russia.
Okay.
Their domestic R&D and fusion, it's just not as active today as it was back in the Soviet era. They made foundational contributions back then.
It's huge contributions, yeah.
But while they're still part of ITER, their own national program hasn't seen the same level of, new device building recently. That's what the source suggests.
And this seems to be where China has really stepped up its efforts, according to these sources anyway.
Oh, absolutely. What's really striking is the expert in that bulletin interview, Dennis White, he makes a very clear statement. He says he believes China now unequivocally surpasses Russia in terms of national capabilities in fusion.
Oh, unequivocally.
Yeah, they've made this a really high domestic priority.
Okay, let's dive into that then. This push from China. The sources paint it as incredibly ambitious.
They really do. It's presented as a clear strategic priority for the government there.
Right.
One source, referencing the American Nuclear Society, notes that China is actively trying to build the entire supply chain needed for a future fusion power industry within its own borders, within its industrial base.
The whole thing, end to end.
Exactly. Their stated goal isn't just, contributing to the science. It's being the first nation to actually achieve commercial fusion power.
And we've all seen the headlines, right? Calling their projects artificial suns, which, let's be honest, is pretty great PR.
It absolutely grabs your attention, and the sources acknowledge that marketing angle. But the expert in the bulletin interview really emphasizes that this effort is much more substantial than just good PR. He calls it a very serious attempt and says they've built real devices that are actually achieving real, relevant fusion experiments. He notes they've rapidly moved into a leadership position globally in fusion science.
And it sounds like they've been pretty clever, pretty strategic about how they've used their involvement in ITER itself.
That's a really key point the sources made. China's an ITER member, right?
Right.
And they've effectively used their commitment to provide in-kind contributions, basically, building and delivering specific components for ITER, like complex superconducting magnets.
Okay.
They've used that process as a way to build up their own internal skills, their own capability to design and construct their own advanced fusion devices back home.
That's smart. Sort of learning by doing on the international stage and applying it domestically.
Exactly,
Yeah.
leveraging that participation.
Okay, let's get into the specifics then, because this is where it gets really fascinating. The sources list some genuinely impressive technical achievements coming out of China recently.
Yeah, the numbers really do highlight the progress. One major project is EAST, the Experimental Advanced Superconducting Tokamak.
Right.
According to the NM and bulletin sources, EAST set a new world record. It contained H-mode plasma for an incredible 1066 seconds.
Wait, 1066 seconds, that's over 17 minutes?
17 minutes, yeah.
Okay, remind us H-mode plasma. What is that, and why is holding it for that long such a big deal?
Right. So think of plasma as that super hot, charged gas where fusion actually happens. H mode, or high confinement mode, is a specific operating state. It's much more efficient.
Okay.
You get way better energy confinement. The heat and particles stay trapped inside for longer, and that's absolutely crucial if you want sustained fusion reactions.
Makes sense.
So holding that H mode state for over 17 minutes on EAST, that's significant because it's a major step towards demonstrating the kind of, prolonged, stable plasma operation you'd need for continuous electricity generation in a power plant, not just these short bursts we used to see.
Got it. So moving towards steady state. And then there's the HL3 device. The CNNC source talks about some major temperature milestones there.
That's right. On HL3, they hit an ion temperature that's the atomic nuclei needing to get hot enough to fuse of 117 million degrees Celsius.
Oh.
And for the first time, they reached an electron temperature of 160 million degrees Celsius.
160 million degrees. I mean, that's just mind-bogglingly hot.
Yeah.
Way hotter than the sun's core.
Way hotter, exactly. And achieving these temperatures, combined with other factors like the plasma density and how long they can confine it, it led to a big jump in what scientists call the fusion triple product.
Okay, the fusion triple product. What does that actually tell us? Why is it important?
The triple product is essentially the key metric. It combines density, temperature, and confinement time. It's the main indicator of how close you are to getting significant, sustained fusion reactions.
So higher is better.
Much better.
Yeah.
A higher triple product means more fuel particles are interacting effectively. And CNNC states that hitting these parameters marks China's fusion research entering the combustion experiment stage.
Combustion experiment stage, meaning
Meaning they're getting closer to demonstrating that the fusion reactions themselves can help sustain the plasma temperature, moving towards a self-heating or burning plasma, which is a critical step.
Okay.
They also report HL3 achieved repetitive discharges with those ion temperatures over 100 million degrees. And CNNC claims this confirms China's leading position in fusion technology based on these performance numbers.
And it's not just about the plasma itself, right? They're also developing all the complex tech around it. The sources list some specific kit they've developed themselves.
Absolutely. That's crucial. The CNNC report highlights their self-developed high-power microwave gyrotron.
Gyrotron? Sounds like something from Star Trek.
Kind of. Think of it as a super powerful microwave generator. It's used to heat and control the plasma with very precise radio frequency waves. Theirs is 2.5 megawatts, which is essential for, fine-tuning that incredibly delicate plasma state.
Okay.
They also have 2 high-power neutral beam injection systems.
Right. What do those do again?
Neutral beam injection. It's another key way to heat the plasma. You fire high-energy neutral atoms into it.
Okay.
Because they're neutral, they can cross the magnetic field lines, then they collide with the plasma particles, transfer their energy, and pump up the temperature and density. Each of their systems is 7 megawatts. And they say this tech puts China among the world leaders in this specific heating method, particularly for heating the ions directly.
So it's a whole suite of really advanced components. Even things like the power supplies get a mention.
Yeah, the CNNC source notes their self-developed high-voltage power supply. You need that for things like the neutral beam injectors. It delivers up to 120 kilovolts DC with really high accuracy, better than 1%.
Which is critical, I imagine.
Absolutely. They highlight it as being at the international forefront for these kinds of power supplies and fusion tech.
And you need incredibly precise ways to actually measure what's going on inside that inferno, right? Diagnostics.
Oh, diagnostics are hugely important and hugely difficult. HL3 uses things like compact Thomson scattering.
Okay, what's that?
It's a technique where you scatter laser light off the electrons in the plasma. By analyzing the scattered light, you can measure the plasma's temperature and density very accurately.
Clever?
And they also have what's described as the world's first set of a triple grating precision spectrometer.
A triple grating precision spectrometer. That sounds intense.
It does. Basically, it's a highly advanced tool for analyzing the light the plasma emits.
Yeah.
It tells you about its composition, temperature, motion with really high precision. The sources claim this device has twice the accuracy of other international versions.
So they're pushing the boundaries on measurement tools, too.
Definitely. Overcoming major technical hurdles in diagnostics. And some of these Chinese-developed technologies have even been adopted by international collaborations, like the ITPA Joint Diagnostic Project.
And their software, their control systems, are those being used elsewhere, too?
Yeah, the sources report that China's own fusion device control system, it's called CODIS, is actually being used in fusion facilities at over 10 different research institutes and universities around the world.
Wow. Okay, so it's exportable tech.
It points to a really robust capability. Even their fueling technology, things like supersonic molecular beam injection, which is a smart way to get fuel particles deep into the plasma efficiently. Even those methods have been standardized and integrated into ISO standards.
So it's really not just one or two flashy records. It's this broad, deep investment across the entire spectrum of fusion technology.
Exactly.
And they're putting serious money behind this, the sources say.
Oh, substantial investment. The NumMi-ion source estimates China's annual investment in fusion is over $1.5 billion.
Billion with a B.
Yes. And the Bulletin interview highlights a specific $1 billion commitment just for a new facility called
Craft.
Comprehensive Research Facility for Fusion Technology. It's due for completion soon, and its focus isn't just the plasma physics. It's about developing all the other critical technologies you need for a power plant.
Like what?
Things like the systems to handle the immense heat, systems to breed tritium fuel inside the reactor, and crucially, how to convert the fusion energy into usable electricity, the whole power plant engineering side.
Got it. And the results are showing up in IP, too. Patents.
Yeah, Wyonan states that China has now accumulated more fusion patents than any other nation.
Okay. So summing all this up, this massive, really integrated push.
Yeah.
What does it tell us about China's motivations? Why pursue fusion so aggressively right now?
Well, the sources lay out a few key drivers. First, there's just the sheer energy demand of China's huge growing economy.
Yeah.
And a clear recognition of the environmental limits and also the geopolitical risks of relying so heavily on coal and other fossil fuels. Energy security is just paramount for them.
Right.
Beyond that, there's clearly an ambition for geopolitical influence.
Right.
If you control the knowledge, the technology, the supply chain for a potentially transformative energy source like fusion, well, that offers significant strategic advantages globally.
Absolutely.
The Bulletin interview even goes so far as to suggest that fusion, alongside maybe AI, could be the two most disruptive technologies of this century.
Wow.
Fundamentally reshaping global power dynamics by changing who has access to abundant, clean energy.
That really reframes things. It shifts the perception of fusion being something way off in the distant future. Which brings us to a broader point, doesn't it? About shifting timelines globally.
It absolutely does. For many years, particularly in the West, there was kind of a sense of waiting for ITER to be finished, waiting for its results before really committing serious money to the engineering challenges of building actual power plants.
The fusion is 30 years away trope.
Exactly. But these sources, especially that Bulletin interview, they emphasize that companies and other nations are simply not waiting anymore. The game has changed.
We're seeing other countries setting much more ambitious near-term goals now.
We are. The U.S., for instance, announced its bold decadal fusion plan back in 2022. Their explicit aim is first prototype fusion power plants in the early 2030s.
Early 2030s. That's soon.
It's very soon. The UK has similar aspirations. They're planning for an electricity-producing fusion plant to come online around the same time ITER is expected to start up.
Interesting. And Japan.
Japan also has a very active program. The expert describes it as coming very quickly. They're accelerating a national plan focused on rapid commercialization, really shifting their focus from pure science towards energy production goals.
So it's not just China then. This acceleration, this drive towards commercial fusion, it's a global thing now.
Correct. The bulletin piece explicitly highlights that multiple entities, not just governments, but also private companies attracting significant venture capital, are now pursuing commercial fusion in earnest. That's a fundamental shift in the landscape compared to even, say, 10 years ago.
Right. And this new optimism, this acceleration,
Hmm.
it's not just political will, is it? It seems grounded in specific technological advancements. The sources point to a couple of breakthroughs as being really key drivers.
Definitely. And one of the most impactful, maybe the most impactful, is in magnet technology.
Okay.
The bulletin interview describes a quantum leap in performance from high-temperature superconductors, specifically materials known as cuprates, over the last 10 years or so.
Okay, high-temperature superconductor.
Yeah.
What does that mean in this context, and how is it a quantum leap?
Well, high temperature here is still pretty cold, but it's relative. They need significantly less extreme cooling than the older superconductors. Think liquid nitrogen temperatures instead of liquid helium, or even warmer.
Easier to handle, presumably.
Much easier, much cheaper to cool. But the quantum leap is really about their performance. These new materials enable magnets that can generate roughly double the magnetic field strength compared to the previous generation, the kind used in ITER, for example.
Doubling the magnetic field strength. Why is that such a massive deal for fusion?
Because of a really crucial bit of physics, the amount of fusion power you can generate in a given volume of plasma, it increases with the strength of the magnetic field raised to the fourth power.
To the fourth power. So if you double the field, that's 2 times 2 times 2 times 2.
Yeah.
A factor of 16 increase in potential power density.
Exactly, 16 times. That kind of improvement can fundamentally change the economics and the physical size of a fusion reactor.
Wow.
The expert estimates this could improve the cost profile by maybe a factor of 40 or 50. It's huge. This breakthrough basically allows researchers and companies to revisit older, maybe more compact reactor designs that just weren't feasible before.
Makes them potentially viable now.
Potentially viable and maybe even cost-effective. Plus, these newer superconductors are also incredibly tolerant to intense magnetic fields and radiation, which is obviously critical inside a reactor.
Okay, so magnets are one huge driver. And AI, machine learning, they're playing a role too.
Absolutely. The sources make it clear that AI and machine learning are already becoming, well, indispensable tools in fusion design and optimization.
How so?
Well, plasma physics is just incredibly complex. You hear it described sometimes as a 10 billion body problem because you've got billions upon billions of charged particles interacting in really complicated ways under intense conditions.
Right.
That kind of complexity is almost tailor-made for machine learning algorithms. They can find patterns and solutions that humans or even traditional simulations might miss.
So AI can help figure out things that are just too difficult to calculate otherwise.
Precisely. Take designing the magnetic coils for a stellarator, which is another type of fusion device with really complex, twisted magnetic fields. There are potentially billions of possible configurations for those coils. AI can rapidly sift through those possibilities, iterating designs to find optimal shapes that would be impossible for humans to figure out manually in a reasonable time frame.
That makes sense.
And the expert notes, the computing power available to the average student today is greater than what the entire international team had when they were designing ITER back in the early 90s.
Incredible.
So that combination, massive computational power plus sophisticated AI, it just fundamentally changes the game for designing and optimizing these complex fusion devices.
And we should probably quickly mention a couple other recent big achievements cited in the sources that have also fueled some of this optimism.
Yeah, definitely worth noting. There's the Joint European Torus, JT, in the UK. They achieved a record energy release, 60 megajoules of fusion energy in a single pulse.
A world record at the time.
Exactly. And then there's the U.S. National Ignition Facility, the IFE. They use lasers, a different approach called inertial confinement, and they achieved net energy gain, meaning for the first time, they got more energy out of the fusion reactions than the laser energy they put into the fuel target itself.
Which was a huge scientific milestone.
Huge. Now, neither of these are continuous power generation yet, and NIF is a very different approach, but they are significant scientific demonstrations that add to the overall momentum.
Okay, so we've heard about incredible progress, really ambitious goals, major technological leaps. There's a lot of optimism swirling around.
There is.
But it's crucial to acknowledge, and the sources do this, that this isn't, a done deal. there are still significant hurdles
Yeah.
and definitely different perspectives out there.
That's very important for balance, yeah. The Bulletin interview actually quotes one of Dennis White's colleagues who expresses a much more cautious view,
Okay.
basically saying that any problem you encounter in fusion is likely to be, quote, 10 times more difficult than the equivalent problem in fission energy.
10 times more difficult.
Wow.
What kind of problems are they talking about?
Well, they mentioned challenges like the long-term effects of intense neutron radiation on the reactor materials.
Right, embrittlement and
Yeah,
stuff.
exactly. That constant bombardment can cause materials to become brittle, swell, or degrade over time. Finding materials that can withstand that for decades is a massive engineering challenge.
And fuel supply,
That's another one. Concerns about the fuel supply, specifically tritium,
which is radioactive hydrogen.
right, the isotope of hydrogen. It's needed for the main fusion reaction people are pursuing, deuterium-tritium, or DT. And one comment in the sources explicitly raises the concern about the limited global supply of tritium currently available. We mostly get it from certain types of fission reactors today.
So we'd need to produce more or breed it inside the fusion reactors themselves.
Which is the plan, but breeding enough tritium efficiently and reliably inside the reactor is another major technological hurdle yet to be fully demonstrated at scale.
And speaking of materials, I noticed something interesting in the sources. A bit of a difference in perspective on critical elements needed for fusion.
Ah, yes, you picked up on that. Dennis White, in the main interview, argues that one of fusion's big advantages is that it doesn't rely on particularly critical elements or rare earths for its fuel or primary materials.
Okay.
However, a comment from Daniel Jaspy in the same publication pushes back slightly.
How so?
He points out that while the fuel might not involve rare earths, those high-temperature superconducting magnets we were just talking about, particularly the REBCO type,
REBCO.
stands for rare earth barium copper oxide. They do contain rare earth elements.
Ah,
And he perhaps pointedly notes, the global supply of those rare earths is largely controlled by China.
that's a fascinating counterpoint presented right there in the source material.
Yeah.
Shows even the experts don't have total consensus on the practical material constraints.
Exactly. It just underscores the complexity here. And ultimately, all the sources agree, the real goal isn't just achieving fusion reactions, it's achieving economic energy.
Right, power that can actually compete.
And the Bulletin interview is very clear. Making fusion economically competitive is harder. It's not a cakewalk and definitely not an assured thing.
And I guess the most straightforward skeptical viewpoint noted is just the simple fact that, to date, no fusion device anywhere has actually produced net electricity,
Right.
meaning generated more electricity overall from the whole plant than the plant itself consumes to run everything, heating the plasma, running magnets, cooling systems, the lot.
Precisely. While NIF showed net energy gain from the fuel target itself, that's a very different thing from a power plant running continuously and putting surplus electricity onto the grid day in, day out. That's the ultimate step for commercial viability, and it hasn't been demonstrated yet.
Okay. So given this mix, rapid tech progress, intense global competition, but also these very real complex challenges, how should we think about the potential timeline? The Bulletin interview offered a helpful analogy, didn't it? Looking back at fission energy.
It did. It suggests, looking back at how fission power developed, you had Enrico Fermi achieving the first controlled, low-power nuclear chain reaction in, the early 1940s? Just a basic scientific demonstration.
Right, under the football stadium.
Exactly. Yet, within about 15 years, the first commercial fission power plants were starting to put electricity onto the grid.
That seems incredibly fast, looking back.
Yeah.
Especially for such a totally new, complex technology at the time.
It really was. And, those early plants, they had significant limitations. Low capacity factors, maybe only running 35–40% of the time initially. Quality control issues in manufacturing.
Sure.
But the analogy is that the technology, its reliability, it improved dramatically over time. Through practical experience, better maintenance, better quality control, the learning curve was steep but fast.
Yeah.
So the idea is that fusion might follow a similar path, moving from the scientific demonstration phase, which we're arguably just entering for net energy, towards integrated engineering systems that improve and become commercially viable through that iterative process of actually building and operating them, learning by doing, essentially.
And the reasons for optimism that fusion could follow a faster trajectory than maybe people thought a decade ago?
Well, as the Bulletin interview sums it up, it's really the combination of two things. First, those recent technological advancements we talked about, especially the game-changing high-temperature superconductors and the power of AI in design and control.
Okay, the tech leaps.
Plus, the fact that you now have this critical mass of serious players, private ventures, national governments like China pursuing this with real resources and very ambitious goals.
And momentum.
Exactly. That combination of enabling technology and serious widespread pursuit that often provides the necessary momentum to overcome big engineering hurdles and drive a complex technology towards the market. It gives fusion, as White Blitz it, a fighting chance to potentially meet those faster timelines people are now discussing.
So just to bring those target timelines back into focus, the ones mentioned in the sources,
Yeah.
we're hearing things like the early 2030s for some initial prototypes or maybe first energy on the grid from some players.
Yeah, those are the kinds of goals being publicly stated now by the US, UK, some private companies.
Alongside ITER's expected operational start, still pegged around 2039.
Correct. Those reflect this new era of accelerated pursuit, really driven by these recent breakthroughs.
Okay.
Yeah.
So as we've seen in this deep dive, the whole quest for fusion energy, it's clearly in a period of really intense activity right now.
Absolutely.
It's marked by these significant technical leaps, especially from magnets and AI. You've got these ambitious national goals, with China making really notable strides, not just in plasma records, but in building that whole underlying industrial and tech base.
A very comprehensive approach.
And substantial global investment from both public funds and private money pouring in.
Yeah.
But at the same time, it's clearly still facing these acknowledged, complex, long-standing challenges: material science, fuel supply, and maybe the biggest one, the ultimate goal of making it actually economically viable.
Yeah, those hurdles haven't disappeared. It definitely feels like we're moving past the phase of purely basic science research, though. We're really pushing towards integrating the complex engineering and industrial capabilities needed to potentially generate power from fusion.
Right.
And players like China are showing a very comprehensive approach, looking at the entire ecosystem needed for that.
Okay, so here's something for you to think about as you process all this. Given the rapid technological advancements we've discussed from these sources, I mean, the potentially game-changing impact of new magnets, the power of AI tackling this incredible complexity, the impressive plasma performance we're seeing from devices like EAST and HL3, and maybe drawing on that historical parallel, fission's surprisingly quick journey from lab experiment to grid power. Will fusion, propelled by all this new momentum, actually surprise the skeptics? Could it achieve commercial viability on these faster timelines now being targeted? Maybe we'll see prototypes producing net energy in the early 2030s, or will those inherent engineering and material challenges, those 10 times harder problems like radiation damage, securing tritium fuel, will they prove more stubborn? Will they push widespread economic fusion power much further out, perhaps even beyond ITER's 2039 milestone? Which way do you think it will go?